Good day students. In this video lecture we are going to discuss regarding the additional issues related to the k-means algorithm. I am breaking this particular video lecture into two videos since we are going to discuss 6 issues in detail. If I cover all 6 issues in a single video lecture, it may be too heavy for you to understand. So three I will cover in this particular video lecture. 3 more I will be covering in the next video lecture. So let us see one by one. First issue is handling the empty clusters. Suppose if we have the empty cluster while doing the k-means algorithm or executing the k-means algorithm, then what are the problems posed by that? So one of the problems with the basic k-means algorithm is empty clusters can be obtained if no points are allocated to a cluster during the assignment step. So when you are assigning the points to the clusters, there are higher chances that one particular cluster may not get any point, or you may think that that centroid may not be a minimum point for that particular set of points. So if this happens, then a strategy is needed to choose a replacement centroid, since otherwise the squared error will be larger than necessary. Since your one centroid will be far away from the set of points, definitely it will contribute to the larger SSC. So one approach is to choose the point that is farthest away from any current centroid. If nothing else, this will eliminate the point that currently contributes to the most of the total squared error. You select the farthest point away from the current centroid. So if nothing happens, it will definitely eliminate the point that is currently contributing to the larger SSC. Another approach is to choose the replacement centroid from the cluster that has the highest SSC. This will typically split the cluster and reduce the overall SSC of the clustering. So you, instead of having the centroid which is causing the empty cluster, you replace that centroid so that it will split the cluster and reduce the overall SSC of the clustering. So these two approaches you can follow when you are having the empty clusters. Next issue which we want to look into is the outliers. We already know that from our previous studies, outlier means one point is completely outstanding. Suppose if we take the income of the persons or the people in the country, then the person having the highest income or the lowest income will be the outlier. So when the squared error criterion is used, outliers can unduly influence the clusters that are found. In particular, when outliers are present, the resulting cluster centroids or prototypes may not be as representative as they otherwise would be. The SSC will be higher as well. Because of this, it is often useful to discover the outliers and eliminate them beforehand. Suppose you can identify the income of the richest person in the country or the world, and you can remove that before you use it for the processing. It is important, however, to appreciate that there are certain clustering applications for which outliers should not be eliminated. When clustering is used for the data compression or the financial analysis, every point must be clustered, as outliers may yield the most interesting points. As I was saying earlier, the richest person in the country, richest person in the world, in some applications, those points may be interesting, and if you eliminate that, it may create some inconvenience. That's why in some applications you may not eliminate, but as far as the processing of the k-means is concerned, you can eliminate it. So if we use the approaches that remove outliers before clustering, we avoid clustering points that will not cluster well. That is why alternatively outliers can also be identified in a post-processing step. So this is regarding the outliers. How do you handle the outliers in a k-means algorithm? It is very simple. If you think that outliers is not having anything to contribute to your particular data points as far as the k-means is concerned, you eliminate that. If you think that applications are having something to be done as far as the outliers are concerned, you can consider it in the post-processing step. Next, reducing the SSE with the post-processing. How you can reduce the sum of squared error with the post-processing. An obvious way to reduce the sum of squared error is to find more cluster. We know that if we use a larger k, you get more number of cluster and you can reduce the SSE. In many cases, we would like to improve the SSE, but we don't want to increase the number of clusters. What does that mean? In the name of reducing the SSE, we don't want to increase the number of clusters. This is often possible because k-means typically converges to a local minimum. Various techniques are available to fix up the resulting clusters in order to produce a clustering that has lower SSE. If we simply go on increasing the number of clusters, there is no meaning for that. The reason is most of your k-means will result in a local minimum. That's why we are using various techniques that can be used to fix up the resulting cluster in order to produce a clustering that has the lower SSE. The strategy is to focus on the individual clusters, since the total SSE is simply the sum of SSE contributed by each cluster. We can change the total SSE by performing various operations on the clusters, such as splitting or merging clusters. Let us see how we can perform that by splitting or merging clusters. One commonly used approach is to alternate cluster splitting and merging phases. During a splitting phase, clusters are divided, while during a merging phase, clusters are combined. Two strategies that decrease the total SSE by increasing the number of clusters are the following. That is, split a cluster. The cluster with largest SSE is usually chosen, and we are going to split, and also we split the cluster with the largest standard deviation for one particular attribute. This can also be used as one criterion for splitting your cluster. Suppose if your particular attribute has a largest standard deviation, then you can use that as one criterion and split a cluster. Introduce a new cluster centroid. This can also be another solution. That is, often point that is farthest from any cluster center is chosen. We can easily determine this if we keep track of the SSE contributed by each point. Another approach is to choose randomly from all the points or from the points with the highest SSE. So you introduce a new cluster centroid and you create a new cluster for that. Two strategies that decrease the number of clusters while trying to minimize the increase in total SSE are the following. That you disperse a cluster or merge the two clusters. So dispersing a clusters, how do we accomplish that? This is accomplished by removing the centroid that corresponds to the cluster and reassigning the points to the other clusters. You disperse the clusters by reassigning the points to the other clusters. Ideally, the cluster that is dispersed should be the one that increase the total SSE the least. When you disperse, your sum of squared errors must be increased the least. Merge the two clusters. Clusters with the closest centroids are typically chosen, although better approach is to measure the correct me, that is it is to merge the two clusters that result in the smallest increase in the total SSE. These two merging strategies are same ones that are used in the hierarchical clustering techniques, which we are going to see in the future lectures. So this brings us to the end of part 1 of the additional issues in k-means, that is handling empty clusters, outliers, and how we can reduce the SSE with the post-processing. In the post-processing, you please remember that you can split a cluster, introduce a new cluster, or you disperse a cluster and or merge the two clusters. The one point you need to remember while you do all these things is your SSE should not shoot up. The increase in SSE should be in such a way that it is very minimum. If your SSE increases very much, then there is no much improvement you are going to gain when you are doing the post processing. So this brings us to the end of the part 1. In the next lecture we will see the 3 more issues, that is in the part 2, updating the centroids incrementally, bisecting the k-means and different types of clusters. Thank you.